Hello again, this is the fifth in a series of presentations on system requirements analysis. This one is from 2001, keeping the focus during requirements analysis, and I'll be covering some specific techniques, issues, things to pay attention to that I'd learned in the prior 8 or 10 years working in requirements analysis. So the things I want to cover, first about stakeholders and boundaries and mission and the critical importance of that. Then using state conditions and specifically logic tables as a means to ensure we've covered everything completely, as I talked about in some of the prior lectures, and ensure completeness. The third one is talking about something that's pretty subtle and doesn't always get considered, which is output conditions can also affect behavior. And so how do we need to characterize what we're doing there in terms of system outputs? Fourth, we get into requirement syntax. This is the beginning. I think this is the first lecture I've done on. It includes what we eventually called structured requirements with some detail. And one of the implications of that in terms of capability statements that have no conditions and therefore are inadequate. The fifth element is about timing, making sure that timing is characterized and what can happen if you fail to identify the timing requirement between when an input condition or trigger is received and the output is supposed to occur. And the last section, accounting for Murphy's Law, things that can go wrong, and this harkens back to the first of the SRA papers from 1995. So let us proceed. First one is keep the mission in focus. It's a reminder to pay attention to what are we trying to accomplish. And we note that requirements analysis can also be applied to organizations, so we can use these techniques with groups of people as well as hardware and software. As we develop more detailed data and decompose the design, we need criteria against which to measure and assess alternatives. So measurement now becomes very important in making sure we've characterized our needs, our missions, our solutions, our requirements in terms of measurable attributes, because we have to establish these measures of effectiveness with respect to the mission. How well is the mission performed, for what cost in terms of resources, people, time, dollars? And finally, beware of introducing clever technology just for the gee whiz factor. Unsophisticated customers may fall for this, but sophisticated customers will want to know how your technology improves value from their perspective. Otherwise, they may be tempted to press any key to continue with a large hammer when the clever technology gets too frustrating. And I'm sure we've all experienced this feeling when the latest software upgrade appeared on our desktop or laptop or phone, and now we had to relearn the system. So we want to keep the focus on what is it we're trying to accomplish. Closely related to that is the issue of stakeholders and system interfaces. We use context diagrams to identify the world associated with the system. These may include environments, other systems, operators, and other people, and generally what we call the stakeholders, those who can affect the success of the project. This group is generally much larger than your customer group and will typically include regulators, safety, manufacturing, testing, and others. I've had several discussions with other people about the use of stakeholder as a descriptor. One person in particular said it brought to mind images of trying to kill the vampire. And in this illustration, Dracula is a stakeholder if he can affect the success of your project. For any requirement I'm tempted to add to a specification, I try to find someone who cares, who's going to check during verification, or who is manifesting the need and is willing to take responsibility for that. Because if I can't relate the requirement to some need by some stakeholder, then maybe it isn't truly a requirement. So that champion of the requirement is the stakeholder for that requirement. Because the context sets the development, operating, maintenance, and disposal environment of our system, we emphasize that the degree to which any stakeholders are missing or their requirements are unquantified is a degree of external risk. That is, it's not controllable by the developer because it's not dependent on how the development is happening. It's fundamental to the problem definition because we're missing something in the problem definition. And that's why it represents risk in the system development. And here's all the bullet points I should have brought down while we were talking. I'm sorry about that. Right, the second area is processing inputs. And I tumbled to using logic tables as a way of ensuring completeness of processing inputs with respect to outputs. So logic tables formally link the input conditions, the stimulus or antecedent, with the output conditions, the response or consequence. And such formal methods have been using logic tables for a long time. And it does help ensure completeness because you clearly identify all possible states of the inputs, and you can ensure that all possible states of the system have been identified and accounted for via a linkage of inputs to outputs. The requirements state machine language, notation, and tools, and I'll give the reference at the end of the presentation, arranges groups of conditions associated with our particular output state. This is similar to dependency or fault trees, where we start with the output, the desired or undesired, and decompose the functional design to determine how that result can be achieved. In this table example, there are two ways to effect a transition. Input conditions 1 and 2 are both true, or input conditions 1 and 3 are both true. Other combinations, such as 2 and 3, do not trigger the new state. What can't be determined with this table is whether or what other outputs may be triggered by these inputs. So requirement state machine language is incomplete in terms of covering all possibilities. And this is analogous, well, sorry. So the other method is what I call bottom-up logic tables, where we create logic tables that completely cover provably the union of input conditions to ensure that it actually equals the universal set. So then we can define common behaviors for groups of inputs. So we don't have to have a unique output. What we have for each combination of inputs, what we have is a defined output for each set of conditions. So since we don't limit our analysis of the inputs to those associated with a specific consequence, we're not going to miss any combinations. In this example, we have a portion of the logic table of 6 bistatic inputs, and there are 64 possible responses, 2 to the 6th. Many of these collapse to common outputs, and the results are all defined down here. And for several input states, the result is driven by 1 or 2 inputs, and the rest are don't care. But we've formally analyzed and documented all the combinations. And since we're starting with the inputs, this is more like a failure modes and effects analysis than a fault tree. A fault tree, you start with a consequence and try and derive the contributors. Failure modes and effects analysis, you start with the failures and try and determine the consequences. And in the FMEA and in the bottom-up logic tables, we can prove completeness of the analysis and the requirements because we've literally covered every combination of sets of inputs. And it is tedious, but I found this was the only way to address input conditions in writing software requirements to ensure I didn't miss anything. And that was the basis for the first paper in the SRA series from 1995. One not well understood situation is don't forget about output conditions, because the impedance associated with an output, whether low or high, may affect the required functionality and the subsequent behavior. And at a minimum, we're going to have to define the assumed impedance so that when we make the measurement, we can determine true false. So we need to also analyze the output conditions as part of the state of the system in the area of impedance. So, for example, short circuits, low impedance, and open circuits, which are high impedance, and electrical circuits have direct analogies in fluids and potential analogies in such areas as radiation shielding, too much or too little. One might also consider communication handshaking as a software analogy, as in, did the intended recipient get the message? If the message is transmitted and no one responds, was it actually sent? Did it go off into a black hole or what? So paying attention to the state of the interface is important in ensuring we have the right requirements definition or a complete requirements definition. Because if you don't get it right, then you may be surprised at the output condition. It's not what you expected. We saw this in one of the systems I was working on, where a sending unit made an assumption about the termination impedance, electrical termination impedance, and they were sure that that had been discussed in a meeting, but it wasn't documented in the interface definition. And at the receiving end, they implemented a different termination impedance. And so the interface didn't work properly. It sent erroneous information because of miscommunication about the termination impedance. And the same thing can happen in these other analogies. So we want to use precise language in text-based specifications. Most of us are still stuck with text-based requirements, and we're using natural language. It's evolved to what I called structured natural language. But even natural language requires a degree of precision in order to be useful and to be consistently interpreted by the requirements engineer, the design engineer, and the verification engineer. The fact that we're documenting the requirements implies that we're attempting to mitigate potential loss of tribal knowledge by writing down the engineering agreements about what the system should be and should do. And any ambiguity in language undercuts this precision. We've adopted a syntax composed of several elements, 4 of which are mandatory, and some of which may not be required. And this will be elaborated in the 2015 paper in some detail, but this was our first attempt at defining this structure, the statement of conditions. And you'll see this in some common standards and the INCOSE requirements writing guides. We eventually opted to put the conditions later because some of these condition statements got to be quite long. The subject, that is the who, the what, which is the verb, what is to be done or what is the characteristic, the performance attribute, the how well, and then any other constraints that scope the implementation, such as interface definition. And these condition statements then can arise directly out of the logic tables. So we can have combination of inputs. You can actually have several different input sets that all lead to a common result. So this is a structured requirement that has a long antecedent and multiple outputs that have to happen concurrently. So upon a set of conditions that are defined, and also this includes an absence of a certain condition. So this is all in that logic table that's referenced from the requirement. Two outputs, two results, provide an RF output on certain ports and limit. So it defines the output conditions on all outputs based on the input state, and they're all measurable and they're all well defined. So this is a meaningful requirement in the context of the system was being defined, even if it doesn't seem like it communicates very well in this presentation. But the key here is we're very clear about the conditions, the subject right here, the shall function, provide RF output, limit RF output. And these are concurrent because they both have to happen at the same time in order to satisfy this requirement. The performance attribute and any associated constraints. So this is the first offering of structured natural language. One implication of this was what I call capability statements that tend not to have condition statements associated with them, like the car shall be capable of 28 miles per gallon. And what I've learned in requirements development is if you don't specify the condition, the supplier only has to come up with one condition of the universe for which their system is compliant, and then they're compliant with the requirement, even if it's not operationally useful. So you meet the requirement, but it's going to frustrate your user or your customer. So my example comes from a TV commercial during the first oil embargo in 1973. Major auto manufacturer demonstrated significant improvement in fuel efficiency using a celebrity in a TV commercial. And he said they were driving from Arizona to California, which is largely downhill, depending on where you start, never exceeding 50 miles per hour. That was very carefully stated. And you can imagine what else they might have done to the automobile, like keep the windows rolled up, so driving at night, overinflating the tires, perhaps, to reduce the rolling resistance. But all those things together enabled this manufacturer to assert a much better mileage rating achievement than one would typically get driving around town. And it was this kind of thing that led to, in the United States, defining a standard for how to measure fuel efficiency or fuel economy in cars. So now we have in the United States EPA ratings, and we have city and highway and combined ratings, so that we can normalize fuel efficiency to a common standard across all models. But prior to this event, there was no standard in that regard. And so just about anything could be asserted because one only had to find one set of conditions under which the requirement was satisfied. So the absence of conditions associated with the requirement renders it almost meaningless. So we have to define how the system will be used and get those requirements, get those conditions in the requirement statements. because if they're missing, then we have an incomplete requirement, and that's likely going to lead to an inadequate design. One of the performance attributes is timing. It's not everything, but it's not nothing. So state-dependent requirements depend on the conditions. So while you're in a certain state, you're supposed to do something. So there really are, so that's one type of a functional requirement. But the more common one is a triggered event. Some input happens that stimulates a behavior. And anytime we have a stimulated behavior, we have to assert a timing element. How soon after that input arrives, or with what delay, and with what tolerances. So failing to include a timing requirement because we don't know is inadequate, because you may find out it really doesn't show up. So I had one example where I failed to put in a timing requirement for a triggered behavior. And when it went to system test, the tester said the behavior was never observed. So I contacted the software people that developed that part of the software and said, how long does it take? They said, well, the function's in there. And I said, well, how long does it take to happen? They said, well, we don't know. I said, well, why not? They said, because there was no requirement. So we put it in the code and we know it works because they tested it, with the trigger, but they couldn't tell me how long it would actually take in real life because there was no timing requirement that forced them to check that. So I learned the hard way. And many of these examples are mistakes I've made in learning about requirements development. So I assert that we always have to have a timing requirement. And now we get into, well, what's the trigger event? So you need to be clear what is triggering the clock. So upon receipt of whatever, and is it, if there are multiple inputs, is it the first one? Is it the last one? Whatever it is. And then determine the tolerances. And this tolerance issue applies not just to timing, but to anything else that's measurable. Is it, for example, a not to exceed, so by tolerance plus 0 minus some value, or an average, or must exceed, so some plus but can't be less than. And if it's some average, is it a bounded set, like it's between two values, or root mean squared, or 3 sigma according to some distribution? You have to define those things in order to have precise language. And it was this sort of discussion that is what led me to investigate fuzzy sets in the prior presentation. We may be tempted to get more precise. This is a mistake, because the more precise, the more expensive, and the more effort to have to prove. So this, for example, will differentiate something that can be done by demonstration versus something that has to be done by instrumented test. For example, if you're driving, how long is a yellow light yellow? Now there are standards for that, and you probably see it's anywhere from a few seconds up to maybe 6 or 8 seconds. And the standard, and I don't remember exactly how it's stated, may say between two values. And then we would, if it's at the second level, then there's an implicit tolerance there. Or we might say it's 5 seconds plus or minus something. And as long as we don't get any more precise than about a half a second in any of those definitions, we can do verification with a stopwatch. But if we say something like it has to be 5 seconds plus or minus 1/10 of a second, now it has to be instrumented. because we can't reliably observe the difference of 1/10 of a second in anything. And I would say anything smaller than 1/2 a second would be subject to debate. But you can check with the human factors people. The point is, precision is expensive because what it drives us to in terms of instrumentation during verification. And it doesn't necessarily add any value. You just want to make sure that the duration of whatever the behavior is fit for purpose and satisfies any parent requirements or standards. The last area is talking about failure. And this is where I started on my SRA presentations in 1995. We tend to focus on the things we want to have done, what we call the go path, the functional decomposition of how the mission will be accomplished. But working with designers has taught me that they're very creative in coming up with what if scenarios based on various input conditions. So if I wish to exert system design control over the behavior, then I must document the preferred outcome and the requirements. But if I wait until the designers pose the questions, then my requirements end up chasing the design. So my preferred solution now is to anticipate all possible what if conditions, what if states during the requirements analysis process. And the bottom-up logic tables are one method of doing this. And in the requirements, this can be done with an equivalent of a case statement. If something happens, then do this. Else, if something else happens, do this. So that would be this lower branch. And you can have as many or branches as you want until you finally get to an else statement, which covers everything left over. In other words, all possible conditions that you didn't previously define a behavior for would be covered by that result. And therefore, so this last one, these antecedents are couched in the language of failing to have a condition or set of conditions. And you saw that in the prior example on structured requirements, failing to receive something. And therefore, when we take the union of all sets of inputs, we know that we have covered all possibilities. And this set of complementary inputs we call the complementary antecedents. The key to completeness, I'll be talking some more about that in the next presentation, is that we can prove that all possible conditions of the universe are covered in the requirements. And I mentioned that in the third SRA, and I'll come back to that in the next one. So some of the references that I used in constructing this, formal methods, as an example of how software has been using formal methods to help define requirements. The requirements state machine language that I got from Heimdall and Levison, from IEEE article, and another article on requirements development. There was some good work being done by the University of British Columbia in 1998 and shortly thereafter of using these structured language constructs. And I'm indebted to them from 1998 and following. And with that, thank you very much. Oh, here's some other references, my prior papers, and the INCOSE Requirements Working Group. These probably aren't the correct URLs anymore, but you can find these articles also in the INCOSE Wiley Symposium proceedings available through incose.org and free for INCOSE members. So thank you for your attention. And just to remind you, 7 things to keep in mind. These are primarily lessons learned from making mistakes. Focus. What's the mission? What's the outcome we're trying to get to? Know the states so we can define all the right behaviors. Don't forget about the outputs because the output conditions may affect system behavior. Structured natural language is useful for making sure you have completely defined the requirement. And don't forget about the conditions, because if you don't have conditions, the requirement can be misinterpreted and easily proven to be satisfied, and you won't get what you need. Don't forget about the timing for the same reasons, and pay attention to the failure conditions. Other inputs that you hadn't thought about, or combinations of inputs for which you may indeed want to prescribe a behavior that wasn't thought about in the go path or mission focus, but is nevertheless critically important for the success of the system. And with that, I thank you very much.